This is College Algebra, Chapter 2, Section 4, Absolute Value Functions. Okay, first of all, let's remember what an absolute value is. The absolute value of x equals x if x is positive, and negative x if x is negative. In other words, whatever is inside the absolute value will make that positive. If it's already positive, it stays positive. If it's negative, it becomes positive. We can also take this concept and broaden it to apply to the absolute value of a function itself. So for an entire function inside an absolute value, the function will remain the same if it's positive to begin with, and it will become positive if it's negative to begin with. Little technology note here, the TI-83 and 84 graphing calculators do have the availability of an absolute value command. In order to find it, you go to the Math menu, then you use your arrow key to the right to the Number menu, and it's the first item on that menu. Now to graph y equals the absolute value of f of x, that graph will be the same as y equals f of x for the values of f of x that are non-negative and reflected across the x-axis for those that are negative. In other words, if you were to graph the function itself without the absolute value, all of the part of it that's above the x-axis will remain the same. The part that's below the x-axis will be reflected across the x-axis. And to do that, all you need to do is to change the y values from negative to positive. The domain will be the same as the domain of the original function. The range will be some subset of the set of numbers from 0 to infinity. In other words, the range will be comprised of positive integers or non-negative integers. Here's an example. We have two graphs. We have y equals x minus 4 squared minus 3. And then we also have the absolute value of that. The absolute value is the graph on the right. Notice that as far as the graphing goes, the parts that are above the x-axis are exactly the same. But the part of the graph on the left that fell below the x-axis has been moved above the x-axis in the graph on the right. The domain for the original graph is all real numbers, and the range is from -3 to infinity. The domain has not changed for the second graph, but the range has changed from 0 to infinity. Okay, now we're going to use the graph of this function to sketch the graph of its absolute value, and you're going to give the domain and range. See if you can do this by yourself. Pause the recording, give it a try, resume the recording to check your answer. Right, here's our graph. You'll notice that all we really did was move the part in pink because that was the part below the x-axis, above the x-axis. Notice the x values for the points have not changed, but the y values have become positive. The domain for both would be all real numbers. The range for the original is -3 to infinity, but the range for our new function is 0 to infinity. Okay, some properties for absolute value. Our first one tells us that if we have two things being multiplied inside an absolute value, we can split them up, put them each in their own absolute value, and multiply them together. Our second property tells us that this also works for division, and again we've got that note that the denominator is not to be 0. Okay, this property just tells us the absolute value of a positive number is the same as the absolute value of its negative. For example, the absolute value of 2 is the same as the absolute value of -2. Okay, this is an unusual property. It says that the absolute value of A plus the absolute value of B is greater than or equal to the absolute value of A plus B. This is called the triangle inequality. If you think about it, it makes sense. If either A or B is negative, then adding them first before you take the absolute value will actually give you a lower sum than if you take the absolute values first and then add them. Okay, we have a little more about properties of absolute value. By the way, I'm recording this out on my porch today because it's such a beautiful day, and so you might hear a little ambient noise from different things going on outside. Hopefully it won't be a distraction. So let's consider this function, y equals the absolute value of 2x plus 11. Okay, we're going to factor out the 2. So we have 2 times x plus 11 over 2. Then we're going to use property 1 to separate the absolute value of 2 from the absolute value of x plus 11 over 2. And the absolute value of 2 is just 2, so we end up with y equals 2 times the absolute value of x plus 11 over 2. Now we're going to use this to help us graph. What we can do is we can start with the graph of y equals the absolute value of x, shift it 11 over 2 units to the left, and then finally apply a vertical stretch by a factor of 2. Now you may be asked to draw a comprehensive graph, and we've talked about this before. If you remember, a comprehensive graph for any function is a graph that shows off the important points. For a line, it would be the intercepts. For an absolute value function, we want to make sure that our graph includes all intercepts and the lowest point on the V-shape of the graph. So any x and y intercepts need to be included as well as the point of the graph. Okay, we're going to do a little practice with solving these. Let's try this one. We've got the absolute value of 2x plus 1, and that equals 7. Now in order to solve this, we need to remember what absolute value means. It's a distance. It's a distance of how far something is away from 0. So according to this, 2x plus 1 must be 7 units away from 0 on a number line. That means that it has to either equal 7 or negative 7. Pause this recording, see if you can solve those two problems. Resume the recording to check your answer. Our solution set is negative 4, 3. At both of these points, the absolute value will equal 7. On a graphing calculator, you can graph the absolute value as y1, 7 is y2, and determine the points of intersection. You'll notice they are negative 4, 3, just like we found analytically. Okay, here's some general rules for solving absolute value equations and inequalities. Okay, read over them. Notice case 1 is what we just did with that example. If you have the absolute value equal to a number, you're going to take the function out of the absolute value, set it equal to that number, but also set it equal to the negative of that number. Cases 2 and 3 deal with greater than and less than with inequalities. For case 2, when you have an absolute value greater than a number, then you're going to solve the absolute value of that being greater than number. You're also going to reverse the inequality and put a negative on it. So you're going to solve ax plus b is greater than k, or ax plus b is less than negative k. Case 3, we have the absolute value of ax plus b is less than k. You're really doing the same thing here, but when it's less than, you can set it up as a 3-part inequality. So ax plus b is actually between negative k and k. If you put an equals under the inequalities, you're going to do the exact same thing. You'll just have the equal underneath it. Okay, give these two problems a try. You're going to solve the inequalities analytically, pause the recording to attempt it, and then resume the recording to check your answer. You'll notice I gave you a little head start on both of these. Okay, there we have our solution sets. Notice we had the same numbers for both problems. It's just the intervals are different because one is a less than and one is a greater than. Okay, now we're going to do the exact same problem we did before, but we're going to do it graphically. We're going to do the equation and then the greater than and the less than. So we're going to start by setting y1 equal to the absolute value of 2x plus 1 and y2 equal to 7. Be sure you find your intersection points and then see if you can figure out how to determine where our solutions are going to be for the greater than and the less than for the inequalities. You can use your work on the previous problem to help you kind of reason it out. Pause the recording to try this and resume the recording to check your answer. Okay, here we have our graph, and we see that our points of intersection are -4 and 3 like we found in the previous problem. So that solves the equation. As far as the inequalities go, for the inequality, the absolute value of 2x plus 1 is less than 7. Notice that the absolute value graph lies below the line 7 in between -4 and 3. So our solution set goes from -4 to 3. And it lies above it outside of that. So when x is less than -4 or x is greater than 3, we have the solution to the absolute value of 2x plus 1 being greater than 7. Okay, let's try these examples. Pause the recording, give them a try, resume the recording to check your answer. Hey, notice that in part A we have an absolute value equal to a negative number. That can never happen, so the solution set is empty. There is no solution. Part B is similar. You can't have an absolute value equal negative. You certainly cannot have one less than a negative. So again, the solution is the empty set. Part C you can solve. However, if you think about it, the absolute value will always be greater than a negative. So the solution set is all real numbers. This is confirmed by the graph. You'll notice the absolute value equation lies completely above the line, -5, meaning that the only possible solution, the only possible problem here with a solution is C, and that will be all real numbers. Now, how do we solve an equation when we have an absolute value on both sides? Well, it's actually not that complicated. The first thing we're going to do is solve it as if it didn't have any absolute value symbols at all. We're going to solve it again. This time we're going to put a negative out in front of the right side of the equation. Now remember, that negative will distribute in and change the signs on everything. Okay, using that information, see if you can solve this problem. Pause the recording, try it out, resume the recording to check your answer. Okay, here we have the two equations we need to solve. Of course, the one on the left is pretty quickly solved. We get 9. The one on the right, notice we're distributing the negative sign, and we get -1. So our solution set is -1 and 9. Okay, let's try solving this one graphically. Pause the recording, give it a try, resume the recording to check your answer. There are really two approaches you can do this graphically. You can set each side equal to y1 and y2 and find the intersection. What they're going to do here is they're actually going to subtract the right-hand side from the left and then find the x-intercepts. And when we graph it, we see that we get -1 and 9, which is what we would expect from our analytical solution. Now try these problems. Pause the recording, give it a try, resume the recording to check your answer. Okay, this is really the same problem we've been doing, but now we're looking at less than and greater than. And for these, when it's less than, you'll notice that the graph goes below the x-axis when it is less than -1 and greater than 9. So that's going to be our solution set for the less than inequality. And it's above the x-axis between -1 and 9, so that will be our solution set for the greater than. Here's another one to try, and they suggest that you use the intersection of graphs method. This is where we're going to set the left-hand side equal to y1, the right-hand side equal to y2, and find where they meet. Pause the recording, give this a try, resume the recording to check your answer. Okay, so we found where the graphs intersected. They seem to meet at -9 and 7, and they put those two values into the problem just to double check. and found out that they do indeed work. So our solution set is -9, 7. Okay, the rest of this video is some problems to try yourself. As you go through them, pause the recording to attempt them and resume the recording to check your answer. Do this for the rest of the video.